In this video, we're going to talk briefly about the two remaining types of vector multiplication. Our third overall type we're going to consider here is our scalar triple product. As the name indicates, our final result is going to be a scalar value. So we can write our equation is A dot the quantity of B cross C. And we're not going to go through a derivation, but we can write this a couple different ways as well. We could also write this as B dot the quantity of C cross A, or we could write it as C dot the quantity of A cross B. And so if you want to have sort of a useful way to remember the order, for this first one, of course, we have A, B, C. Of course, we have dot product and cross product in there. But from going to our first instance of the equation to the second, we can just think of moving this A to sort of the end of the chain. And what that gives us then is B, C, A. And we, of course, keep the dot product and the cross product in the same place. So dot product here, cross product here. For going to our last form of the equation, again, we just move this first term to the end, and we get C, A, B. So that's how you can sort of remember this relationship. Another way that we can write this is using sort of our two definitions for dot product and cross product. We can say that A dot B cross C is equal to the determinant of a 3 by 3 matrix, where our first row is our components of A. So we have AX, AY, AZ. Our second row is our components of B, so BX, BY, and BZ. And then finally, in our third row, we have CX, CY, and CZ. And so again, the final result is a scalar value. Sort of an interesting geometrical note is that this scalar triple product represents the volume of a parallelepiped. So volume of a parallelepiped with edges A, B, and C. Our fourth type of vector multiplication that we're going to consider is called our vector triple product. And so as the name suggests, in this case, our final result is going to be a vector. So considering our four types of vector multiplication, two of them give us scalar quantities and two of them give us vector quantities. And so our equation here is if we have A cross the quantity of B cross C, we can simplify that and say that this is equal to B times A dot C minus C times the quantity of A dot B. And so as sort of a useful way to remember this, we can think of this as the back cab rule. So back cab rule. And of course that back cab relates our terms and the order of them on the right side of the equation. And hopefully you can remember on the left side of the equation we just have A cross B cross C. Okay, so a couple notes. Of course, we said that this is a vector triple product, so our end result is a vector. Well, of course, we can say that our A dot C, by definition of dot product, as well as our A dot B, are just going to be scalar values. So these are scalars. We can also point out some properties that we talked about with our dot products in terms of evaluating that right side. So note that if we have A dot B times C, that is not equal to A times the quantity of B dot C. So we can't change around which vectors are being incorporated in that dot product in the parentheses. We can, however, change around where we write the scalar. So for instance, if we had this A dot B times C, of course we could rewrite that and say that's just C times A dot B. So as I mentioned previously, we have two of these types of vector multiplication that we're going to use more often. So types 1 and 2, so our dot product, which was type 1, and our cross product, which is type 2, are going to be used more often. And then our scalar triple product 3 and our vector triple product 4, which we talked about in this video, are going to be more for just using to create shortcuts in our work. Will be used to make shortcuts. So basically just to make our problem solving steps a little more convenient. And we're going to see what that looks like in some examples later on.